Hello everyone, I welcome you all to JK Tech Solution YouTube channel. Today, in our video, we are going to discuss about types of antenna array using HFSS. So before getting into our session, we need to know what is meant by antenna array. So antenna array is nothing but arranging the multiple antennas to increase the directivity. So that is nothing but antenna array. So why we need to improve the directivity? So the directivity is nothing but the ratio of maximum radiation intensity to the average radiation intensity. We need to know what is meant by radiation intensity here. So radiation intensity is nothing but the maximum power that is radiating from the antenna per unit solid angle is called as radiation intensity. So here basically we have three types of array antenna, that is broadside antenna array, end-fire antenna array, and then collinear array. So these are all the three types of array antenna we have. So in broadside array, all the antennas are placed perpendicular to the array axis, and then we have an maximum radiation pattern perpendicular to the array axis. So that is what we have obtained the radiation pattern also we have obtained the here. And then coming to end-fire antenna array, this end-fire antenna array, the antennas are arranged along the line, and they also possess the radiation pattern along the line. So the maximum radiation pattern will be having at the along the line. So the major difference between the broadside antenna array and end-fire antenna is that in broadside antenna array, we are going to give equal current and equal phase. So, but when you take end-fire array antenna, we are going to have equal magnitude, but only change we are going to have is phase. Okay, 180 degree out of phase. So it is nothing but end-fire antenna array. Okay, so here we are obtaining the maximum radiation direction along the line, whereas in a broadside antenna array we are obtain the maximum radiation density perpendicular to the array. So sorry, perpendicular to the line. Okay, line of axis. So this is what a major difference between broadside antenna array and then end-fire antenna array. So coming to collinear array. So collinear array nothing but we have two types here: vertical and horizontal. Okay, when you take vertical, the antennas are arranged in vertical manner. Okay, so here we obtain the maximum radiation. Direction of maximum radiation along the line, whereas when you take horizontal, we will be obtaining the maximum radiation perpendicular to the line. So this is what a major difference. This is what collinear. There are two types: vertical and horizontal. This is what the types. So in this video, we are going to design a array antenna. So in the previous video, we have already designed the dipole antenna. So in the same way, we are going to just make multiple dipole antennas, and we are going to make the array antenna. So for making the array antenna, here we can see here, there is some space here left on it. Okay, so there is a space between two antenna. So here the space that is, what the space that we are going to give here is lambda by 2. Okay, so for each and every space we are going to assign lambda by 2. You can give lambda by 2 or lambda by 4, it's our convenience. Okay, so here we have an online tool called antenna calculator or blogspot.com. So I have also provided the QR code in the here, and I also provided a calculator link in the description box, okay, as well as in the comment section. You can refer it. So now we can just discuss how to find the half-line. So here we are in this video, I am taking half-line wavelengths. Okay, distance between two successive antenna or array element is 57.6.65. I just show you how to use this antenna calculator. So I just open antenna calculator blogspot.com. Here you need to click the first link, wavelength calculator. So after clicking the link, so here they have just provided some theory part, what is wavelength, frequency, and the formula for wavelength, that is lambda equal to C by F. They have just provided, and here only we need to enter the frequency. So by default they have said gigahertz. Okay, you can either change to megahertz or kilohertz. So here you need to enter. In this video I have taken the frequency as 2.6 gigahertz. So I am entering here frequency 2.6 gigahertz. So for 2.6 gigahertz, the wavelength is 115.3048. and the half wavelength is 57.6524, and quarter wavelength is 28.8268. In this video, I am going to take half wavelength in millimeter, 57.6524. This is what the half wavelength I am going to take in this video. So I have mentioned here half wavelength as 57.65 millimeter. So let's enter into simulation part here. So I've already in the previous video, we have designed a dipole antenna at 2.6 gigahertz. Should just show the result here. Create model result, create model resolution report, rectangular plot. Yeah, here we have obtained the S parameter plot. Okay, so S parameter plot we have obtained at 2.6 gigahertz. Okay, 2.6 gigahertz. So now we are going to design an array antenna. Okay, so first you need to open the previous video. We have already designed this dipole antenna. So we are just going to make this as an array antenna. So to increase the directivity. Okay, so I'm just, so first of all, there is a radiation box. Okay, and just click here this, and then you just click the cross mark. Okay, so that it won't disturb us. So first of what we are going to do here, click on HFSS and just check the solution type. It has any change here in the solution type HFSS options, network analysis and model should be clicked. Okay, then click OK. Then what we need to do here is click on you need to click on dipole and then click the control and then click port. Okay, so when you click this dipole and then the port, you can see the pink color thing is formed. Okay, so here you need to give duplicate along the line. Okay, so duplicate along the line, the top, the draw model, the top, it is having duplicate along the line. Just click this duplicate along the line. A solution exists. Do you want to create a non-model object? Yes, you need to click on yes. So after clicking that, you need to click on the center point. Okay, so just click on the center point and then move this along the line. Okay, we need to move this because we are going to design antenna along the line. So just move it along the line and then just click left click. Okay. Okay. Here it will ask duplicate all into how many objects we need. Here we are going to design the 8 element array antenna. So I am giving the total as 8. Okay, so I have given total number as 8 and then just click OK. So as you can see here, totally 8 elements are created. 1, 2, 3, 4, 5, 6, 7, 8. 8 element array is created here. Okay, so here what we need to do here is we need to adjust the length. Okay, as I have shown you in the wavelength calculator for 2.6 gigahertz, I am keeping here the distance between two suction antennas. So as you can see here, there is a distance between these two element array. Okay, that is antennas, and then there is a distance. So we need to keep the distance for it. Okay, for that only I have calculated using antenna calculator blogspot.com for 2.6 gigahertz. For me, the half wavelength is 57.6524. Okay, I am taking this value half wavelength 57.6524. So I'm going to just enter. So in the dipole, click duplicate along the line. And then here instead of 0.6, you need to enter 57 point, I think what value I have 9, 57.6524. 57.6524. Okay, I have entered a value, give apply and then OK. So after this, you can see here the 8 elements are separated by the distance, that is 57.6524. Okay, so now we are going to obtain, now as you can see here, the port whatever we have assigned is just like this. Okay, for here also we need to click duplicate along the line. Here you need 0.6, 57 point, as you can see here, 57.6524. 57.6524. Click on apply and then OK. So now you can see here there are 8 element antenna element array is created, and also here you can see the port is also assigned to the individual 8 element array. The next step what we are going to do here is to assign, as you can see here, in the first element array already we have assigned excitation, but as you can see in the second element array, okay, so as you can dipole 2, dipole antenna 2, but here we don't have an excitation. Here we have only single excitation. So we need to create an excitation for all 8 elements in array. Okay, so just we create that. So for that, what we need to do here is just click on port 2. Port 2, 3. Okay, for port 1 already we have port section. We already have a lumped port. For whereas for port 2 we don't have. Okay. Okay, click on port 2, edit, scale. Sorry, not scale. Surface, edit, surface, section, Y Z. Okay, click on OK. Similarly, need to give for all the objects. For port 2, we have given port 3, edit, surface, section, Y Z. Okay, for port 3, I have done. Then for port 4, edit, surface, section, Y Z. Then for port 5, edit, surface section YZ. Then for port 6, edit, surface section YZ. Similarly, you need to give for all the ports. Successfully given the port. We need to change the individual here. It is showing non-model, so we need to model this. Click on dipole and then give model like this. For all the dipole, we need to give like this model. Okay. Applying the port is also non-model. So if it is non-model, then there is some error showing when we are simulating. So for port also, I'm giving the model option. Okay. For all the ports and the antenna, we have given the model. Okay. So for port 2 section, okay, we have for excitation what we are going to give here also it is non-model. Okay, for there is an error. If we simulate with this non-model, then there will be error when we simulate. So here also I'm giving the model. Okay, so click on this, apply. Okay, port 3 section, left click, model, apply. Okay. Our 8 ports as well as for antenna and as well as for excitation where we are going to give, we have just model. Okay, we have just given the model option so that you won't get error when we are simulating. Okay, so because when you give validation check, there will be error before when you non-model this, but after modeling this, uh, it is showing green tick. So then our design is correct. Okay, so we can give excitation for individual ports. Okay, for our first port already the excitation is given as you can see here. You can click on excitation here as you can see this green color mark. Okay, hence the excitation is given. But for the second antenna, we have not yet given the excitation. Okay, click on this port 2. Okay. So for port 2, we have not yet given the excitation. So here we need to provide excitation. So click on port 2 section 1. Okay, click right click on it, assign excitation, port, lumped port. Before getting it, we need to check the arrow mark for first one. Okay, just check it. Otherwise, there will be some error when you are doing. So in port display, we have given the arrow mark in the upside. Okay, so in the same way, you need to give for all the things. Okay, otherwise there will be error. Okay, assign excitation, port, lumped port, 50 ohm. Okay, in the previous video, we have given full port impedance as 73, but here we are going to give it as 50 ohm. Next, new line. Okay, define. Next, 50 ohm, finish. So similarly, we are going to give for all the ports. Okay, with all. So for port 2, we have given, and for port 3, we have successfully assigned. Now we are going to give for port 3. Okay, for port 3, similarly, click on port 3 section 1, assign excitation, port, lumped port, 50 ohm impedance, new line. Click on this. Okay, define 50 ohm as input impedance. Similarly, we are going to give it for all the ports. Okay, so we have given it for port 3 ports. We have given the excitation. Next, for a 4th port, we are going to give for port 4. So for port 4, so for port 4, assign excitation port. In the video, we are going to give for all the ports. Okay, for port 5, dipole 5. It's not showing. So here I am assigning the excitation. Okay, so for port 5 section 1, assign excitation port, lumped port, 50 ohm as input impedance, new line. Click on here. Okay, define. Port 6, we are assigning the excitation. Okay, assign excitation port, lumped port, 50 ohm as full port impedance, new line. Then we are providing port impedance. And then for port 7, okay, so for port 7, we are giving the excitation, assign excitation port, lumped port, 50 ohm as input impedance, new line. Click on here. Okay. Port 8, we are giving assigning the excitation. This is 8 element of an array. Okay, last but not the least. So click on port 8 section 1, assign excitation port, lumped port, 50 ohm as full port impedance, new line. Starting from the bottom and see here we have assigned excitation for all the 8 element array. Okay, 8 element of an array antenna. Okay, so now what we need to give radiation surface. Okay, just click the radiation surface and the green mark here. Okay, so after giving it, our radiation surface is created. So now what we are going to give is initial. We need to check the mesh settings. So click on mesh, initial mesh settings. So if the initial mesh settings is high, then there will be some error in it. So just move down the mesh into 2. Okay, I have given it for 2. Okay, so then click OK. So we have successfully designed our array antenna. Okay, using dipole antenna. So now we are going to give validation check. Okay, I have given the validation check. Okay, check the plots. So the above steps, the design of dipole antenna, I have given the previous video. In this video, we are making the array antenna. Okay, so you have successfully assigned the ports, lumped ports, as well as the we have duplicated all the antennas. Okay, so we have created 8 element array antennas. Okay, so here so that only 8 excitations are created. So now click on HFSS validation check. Been marked okay. Then click analyze all. Now our design is simulating right now. We can wait. We need to wait for 1 or 2 minutes for simulation. Okay. take 5 to 10 minutes for simulation. We need to wait for it. Okay. Simulation is successfully completed. Now we have to just we can see the result. Click on HFSS results. Create model solution terminal report rectangular plot. So S11 parameter in decibel. Click on new report. Our antenna is our antenna array is successfully simulated at 2.56 gigahertz. Okay, as you can see here, 2.55 nearly it's equal to 2.6. Okay. So now we can obtain the gain plot right now. So for obtaining the gain plot, we need to change some parameters here. Okay, so we can just change this right now. So now we need to click on 3D. Okay, so we need to click on 3D. Sorry. Now we need to click on 3D. Okay, so we have obtained the frequency at 2.5 gigahertz at minus 14 dB as written last. So now we need to click in the radiation. Okay, in the antenna HFS design model network. Click on radiation 3D. Here you need to give the start and then stop angle. Okay, so for the first thing I am giving the start angle as 0 degree. I'm in the stop angle as 360 degree. Okay, so then here for phi I have given 0 to 360. For theta I am providing the 90 degree. So after this, click on OK. So now we can obtain the radiation pattern. Okay, so click on HFSS results, create far fields report. Here radiation pattern. So here we need to click on instead of theta phi gain, and then for families you need to click for select values 90 degree. Okay, for theta you need to click for 90 degree and then just click new report. So here we have obtained a radiation pattern, but we have not provided the magnitude value here. So for that we need to click on field overlays, click on edit sources, and then you need to provide a value for all the thing 1. For magnitude you need to provide for 1, 1, 1, 1, 1. Okay, for all the thing you need to provide the value as 1. Okay, so after providing 1, you need to click on apply. Okay. So now as you can see here, now we have obtained the radiation pattern for broadside array. So for broadside array, we have discussed in the slide that go now slide. So so for broadside array, as we have discussed in our presentation, that there is a maximum radiation perpendicular to the array axis. So similarly, we have obtained the radiation pattern maximum to the perpendicular to the array axis. Okay. So now we can obtain results, create far fields report, not radiation but then 3D polar plot. Similarly, phi theta new report. So as you can obtain the given diagram in a 3D plot. Okay. So this is what our append one. So now we have to verify our parameters for broadside array. We have verified. Then we need to verify for end-fire array. As you can see, for end-fire array, their maximum radiation is obtained along the line. Okay. So for that, what you need to give? You just click on field overlays and then click edit sources. For as you all know that for end-fire array, there is a 180-degree phase shift between two elements of array. So for that, I am giving the phase as 180 degree. For each alternate elements, I'm giving it as 180-degree phase shift, but the magnitudes are equal. Okay, I'm giving equal magnitude. Okay, then click on apply. Okay, so now we need to check our gain plot. So now, as you can see here, the gain plot is obtained. Maximum radiation is obtained along the line. Okay, so as you can see, the major lobe is obtained maximum, so that we can verify that our antenna is our antenna directivity is so high. Okay, so here we can also obtain the directivity pattern. Okay, results, create far fields report, radiation pattern. You can obtain the directivity plot also. Okay, sorry, instead of theta, you need to give 5. Okay, so I not given 5. So as you can see, the radiation pattern we have obtained successfully right now. Okay, you can obtain RE plot. Okay, so these are the parameters we have obtained without decibel. So with the decibel, we need to obtain a gain total. dB is present, so just need to give dB and then click on new report. So here we have obtained the parameters with dB, and we can also obtain the gain parameters without dB also. So these are all the major lobe, and the back one is a back lobe, and we have obtained the side lobe as well as the back lobe. Okay, so this is how we have verified the parameters. Okay, once you change, okay, so here I have given 180-degree phase shift, so that I have obtained the radiation pattern maximum along the line. But when you change this to, okay, not here, when you click on field overlays, okay, and you check edit sources and you give 0 degree, okay, you give same phase, okay, for 180-degree phase shift, you have obtained maximum radiation line. Once if you give 0, okay, same phase shift, okay, then you want to apply, okay. Now you can see the maximum radiation is obtained perpendicular to the array line. So this is what we have verified the end-fire array and then broadside array parameters. Okay, so this is what we have verified. The next, so I have successfully verified. Okay, so next we need to verify the collinear array. Okay, so we can do this in next part. Okay. Okay, thank you so much for watching the video, and I hope you to see you again in next video. Thank you. Have a nice day.